can't. All right, I want to talk about mass. We're dealing with mass. And the thing we've been dealing with lately is something called molar mass. You should have a note, have a record, if I write with a marker, there we go, of what molar mass actually means, okay? So molar mass is in grams, all right? And what it is the mass of 1 mole. We know this, I think. And we know how to calculate it. That's what we've been working on, mass of 1 mole. So for example, if I just took any old element, let's see, what I haven't used recently, calcium, all right? So what is the molar mass? The mass of 1 mole of calcium. This is just an element. It's just a symbol. It's not more than one symbol stuck together or anything like that. Just one symbol, calcium. So that's really easy. All we do is we look on the periodic table and look up the atomic mass, which is actually in these units called atomic mass units, really small units. But we're putting it in grams that we can deal with. And it says on the periodic table, it says 40.078, which I told you guys when we do these masses, I want you to round off to 2 decimal places. Actually, I think I've got a different periodic table than you. Yours says, does yours just say 40.07? 40.08. Okay. Pizza cake then. Calcium. 40.08 grams. And then I told you guys I really wanted you to get used to writing this over 1 mole so you know that we're talking about grams per mole. And I want you to really get comfortable with that. Grams per mole. If it's gram, I should just say to you, what does grams per mole mean? You're saying you're probably dealing with molar mass then. Okay? Grams per mole. I mean, that's what it is. How many grams per mole? In this case, 40.08. If it was some other element, it'd be a different number. But for calcium, according to the periodic table, 40.08. Now we don't always have just nice little easy elements. Sometimes we have more than one thing, like we might have table salt, sodium chloride. All right, so sodium chloride, table salt. And so what we have to do is when we have more than one element, we're just going to count the number of atoms of each. So in this formula here, we've got Na, no subscript attached to the bottom right. So that means there's just one Na. And then we have Cl, there's another capital letter, right? So that's a new element, Cl. No subscript, so it's just Cl. And I'm going to take those masses from the periodic table. Na is 22.99 grams. And Cl is 35.45. And we just add them together, that's right. Did you do that yet, Daviante? Slacking. 10, 14, 8. So you should get 58.44 grams, again, grams per 1 mole. Okay, so that means that's a mass of 1 mole of NaCl would just be 58.44 grams per mole. How many grams per mole? 58.44 grams per 1 mole. Sometimes they're even more difficult than that. Maybe we have Maybe we have sodium oxide, Na2O. Okay, so whenever we have a subscript, we have to take that into account. This time there's not just one Na, there are 2 Nas. So I can do this a couple different ways. The way I like to do it is just write down what's in it, and then how many times. So sodium's going to be 2 times, and oxygen is 1 time because there's just one of them. I like to do it that way personally. But I can do it both ways. And I can also do it this way. Just write Na twice, and then O. And then I just write in the masses. So Na is 22.99. We just saw that. And oxygen is 16.00. So if I do two NAs, it would actually be 45.98. Cool. And then the one oxygen is just going to be 16. 61.98. Oh, I already gave you that one, didn't I? We did that as a journal yesterday, didn't we? All right, that's how you do it. This is how we do it. Sounded just like it, didn't it? No. Same thing. I mean, if we did the same thing over here, you get the same answer. 22.99 grams, 22.99 grams, and 16.00 grams. And those would all add up to 61.98 grams. So whatever way you're most comfortable with, I think this one on the left side probably involves a little less writing maybe. Okay, so you're probably sitting there right now going, yeah, Mr. Dodds, we just did this yesterday for a journal, and we showed you that we all know this. But I wanted you to have it in your notes. And that's not the only thing. We're doing this for a reason. We're not doing it just so we can tell people that we can find molar mass. We're doing this because the real idea is that we want to be able to take the mass, ultimately, take that and convert it into the number of particles, which we have done already. But we need to practice it. We did it in the chalk lab when you guys wrote your names in chalk. You found the amount of chalk that you used, and you had to take that all the way down to the number of atoms. But I bet if I asked you for a journal question today to take a certain mass and take it all the way down to the number of atoms, there probably wouldn't have been a whole lot of people that could do it. Maybe one or two, maybe. All right? That's not a knock on you, it's just that we haven't practiced it much. The idea is really you're going to encounter this thing that we call the mole map that you're going to be using a lot. And what the mole map does, the reason it's called mole map, is it shows us the significance of this unit called the mole. The mole is the centerpiece. Because if we can get to this unit, the mole, we can convert to anything else. If I have the number of particles, I can tell you the mass. If I have the mass, I can tell you the number of particles. I can tell you the number of liters. I can convert to moles of another substance in a chemical reaction. I can do all sorts of stuff. And so really what we're going to be doing is trying to go from mass to moles, and then from moles, we can go to particles. Now, since we call this a mole roadmap, I think of those arrows as roads. What roads do we need to take to get from one place to another? If I want to go from the town of Mass, to moles, and then I want to go from moles to particles, it's just like reading a map, which probably nobody in here can do since you guys have had navigation all your life and you don't drive because you guys are only 12, 13. All right, but here's the roads. What they are is they're conversion factors. If I want to go from moles to particles, if I know the number of moles, all I have to do is multiply by Avogadro's number, right? You're familiar with that. That's all you got to do. And then we've kind of been practicing, you saw a little bit, how if we have the mass and we use the molar mass, which we're actually going to have to use it inverted. I'll put molar mass in there. All right, inverted. So instead of saying grams per mole, we're going to say the 1 mole over the grams. Just like this up here. all I'm doing, like if I was using this, I would just say instead 1 mole per 61.98 grams. All right? But we're still going to set up those equations the same way we did before. We're going to take our start or whatever, and in this case, we're going to be starting with grams. So that means we want to have grams down here, right? That means we're going to take our molar mass and flip it upside down. And from there, if we want to go on further, well, if I've got mole at the top there, I'm going to put mole here, which means Avogadro's number's got to go up there. RP for representative particles. Atoms or molecules, if you will, right? So I'm going to hit pause on there real quick. Okay, so what I did is I just gave you the next worksheet we're working on. And I just went over the new success criteria that we can calculate the number of particles in a given mass, which means you're going to be given a mass, and you're going to be able to find out the number of atoms or molecules within that mass. Okay? Some of these questions are going to go the other way. We're going to see some examples of both. They could say if you have this many atoms or this many molecules, particles, what would the mass be? Go the other direction. Maybe they have you stop at moles and just find moles. That's even easier. But the real idea is that we can take a mass and we can get to moles and moles to particles. So the worksheet you just received is titled Moles, Mass, and Particles Worksheet. All right, so we're going to do a couple of these together so you see how it works. So number one. So just like I told you guys, with any of these story problems, we want to just see what's given. What are they telling us that we have? Because that's always going to be the start of our problem. It's also not a bad idea to pay attention to where we want to go to. So maybe we even want to record these. It's up to you, but I think it's a good idea. Maybe we want to pay attention to our target, where we're going to. Okay? So what do they tell us? What amount do they give us in number one? They tell me there's 24 Gs of FeF3. There's 24 grams of FeF3. So I'm going to write that down for the start. 24 grams of FeF3. What are they asking me to find? Formula units, which I told you guys, whenever you see formula units, I just want you thinking molecules. So I'll put a question mark, molecules. Formula units, think of the same thing. It's just formula units are technically what you should say if you're dealing with ionic compounds, which is what this would be, okay? But it's a similar idea to molecules, all right? All right, so the reason I made 24 grams of FeF3 my start is because that's going to be my start. So I'm going to write 24 grams. And it's important that we include what it is as well of FeF3. And I'm just going to put that over 1 to start. That's how we do our start. Our start is always over just 1. Some people get confused, I notice, too. When you're setting up your equation, you're like, wait a minute, what do I put under the start? Nothing. Just 1. Just leave it as that thing. Okay, don't put anything under the start. 1 means it's just that thing, right? Times. Okay, so using our knowledge of setting up equations, we should know that whatever unit we have, we're going to put that on the bottom of the second one, right? So if I have grams of FeF3, I want that same thing right here. Okay? Now, that map I was talking about, we only have two possible conversion factors that we can use. We can use Avogadro's number, that's when we're dealing with something to do with particles, or we can use molar mass, and that's when we're dealing with mass. Okay? Grams are units for what? Mass, right? So if we're dealing with grams, we're dealing with mass, that means I'm going to be dealing with the molar mass. Okay, if we're dealing with grams, we're dealing with mass, means we're going to be using the molar mass. So I got to find the molar mass of Fe, F3. So Fe, how many of those do I have in the formula? 1. And F, how many of those do I have? All right, cool. Let's look up their masses. So Fe has a mass of 55.85. And F has a mass of 19. So that would be 57. Yeah? Is that right? 3 times 19? Okay. And then 1 times 55.85 is just 55.85. So what's 55.85 plus 57? Thank you. Okay. So there are 112.85 grams per 1 mole if we're talking about FeF3. Okay. Now we know that we want the grams though to be on the bottom. So this is why I said we got to invert it. So instead of saying 112.85 grams per 1 mole, we're going to say 1 mole per 112.85 grams. Does that make sense? Why am I doing that again? Because I know grams have to be on the bottom because it was on the top of the first thing. So 1 mole over 112.85 grams. So far, so good. Stop me at any time. Something, I know I've been there, guys. Remember, I was in high school just like 6, 7 years ago. I remember sitting there and math teacher doing something that I actually understood, but just because they did something a certain way, I went, wait a minute, what? Why? Oh, thanks for telling me. Thanks for clearing that up. So it might not, don't worry, just ask a question if something doesn't make sense. It might be something silly. That's okay. Just make sure every step of the way you go, yeah, I understand that, understand that. Okay, and of course, if we have certain units on top and on bottom, then they cancel out, right? So that means my grams of FeF3 are now gone. This is, I should put moles of FeF3, by the way. But grams of FeF3 are gone. They canceled out. I still have my numbers. Numbers are still there. Numbers don't cancel out, right? Just the units. Now, I'm actually going to stop here and solve because I just want to break this down from grams. Let's just get it to moles first. So let's stop there and look at what we got. All right? So all I'm doing is I'm taking that 24 grams of FeF3. I want to know how many moles that would be. I know there's 24 grams in 1 mole. So do you guys think I have more than a mole or less than a mole? Less? How many grams would I have if I had a mole? How many grams of FeF3 would I have if I had 1 mole? 112.85, right? Do I have that much? I do? What do we? No, we had 24 grams, right? That's only like, what, like not even a sixth of that? Okay, so it's probably going to be like a sixth of a mole. Just a guess. Let's take a look, shall we? If I multiply across the top, I'm going to get 24 times 1 mole of FeF3. That means I'm going to have 24 moles of FeF3. Not really. That's just our top answer. Then I'm going to multiply across the bottom. 1 times 112.85, which is just going to be 112.85. And now what I'm going to do is I'm going to take the 24 and divide by 112.85. 0.212. So yeah, it's more than a fifth, less than a sixth. 0.2, let's go, well, they only gave us 2 numbers, so I'll leave it at 2. So 0.21 moles of FeF3. Now this doesn't quite answer the problem, but what we did find is we found out how many moles of FeF3 we have. Okay? So now we can use Avogadro's number because we know that there are going to be 6.02 times 10 to the 23rd molecules, or formula units, in 1 mole. All right? So do we expect to have that many? Do you think we're going to have 6.02 times 10 to the 23rd molecules? No, we're going to have a little more than a fifth of that, less than a sixth, about 2/1 of that, right? So really what we can do here is we can just start a new problem. I'm going to take that number of moles, 0.21 moles of FeF3, and I'm going to make that my start, okay? I know how many moles I have, but we're still trying to keep going so we can find the number of molecules. All right, so I'm going to multiply it by something. I don't know anything about this thing except for I do know one thing. What do I know? Moles has to be on the bottom. Moles of FeF3 is up there. It's got to be down here. What's that? That's a good idea to always write the substance with it. All right? And what do we say we're trying to do here? What's the purpose? We know how many moles, and we want to try to find what? The number of molecules, particles, right? So, and I just asked you a question. Do you think we're going to have, you know, 6.02 times 10 to the 23rd molecules? Do you think we're going to have more than that? Do you think we're going to have less than that? We can, the whole idea is we can get an idea in our head about how many particles we're going to get. But the main idea is we know we're talking about particles. So whenever we're talking about particles, we know that we're going to use that Avogadro's number. Okay? So I know I'm not going to put 6.02 down here on the bottom because all these conversion factors are like just some number per mole, right? So that means Avogadro's number is going to have to go on top. And my substance I'm dealing with here, that I know what I'm dealing with because I keep writing it down, is FeF3. So would those representative particles be atoms or would they be molecules? They are going to be molecules, right? So now I know that the moles of FeF3 have canceled out. The only thing I have is molecules. That's good. That's what I want to find. And so I'm going to take 0.21. I'm going to multiply the normal number times the normal part of Avogadro's number. 1.26. Thank you. We'll call it 1.3. Don't forget to write your times 10 to the 23rd. Okay? The weird part. So multiply the normal parts normally and add, tack on the times 10 part. Molecules of FeF3. And it's already in proper scientific notation, so I don't have to worry about changing that around at all. We're good to go. So that is what we have to do. Now that seemed like a lot, didn't it? Okay. Let me show you another thing that we could have done, just so you can see. Some people prefer to break it down into steps like this. But what you could have also done was that first part you had, where you started with the 24 grams over 1, and then we used the molar mass, which was 112.85 grams of FeF3 per 1 mole FeF3. Instead of stopping there and finding an answer, I could have just written down times and kept going, and then just put 6.02 times 10 to the 23rd molecules here, and just did the same thing. Grams on top and on bottom cancel, moles on top and on bottom cancel, and I'm left with molecules. And if I multiply across the top, I'm going to get 24 times 6.02, and then times 10 to the 23rd. And that's going to be over 112.85, but it's still going to come out to be 1.3 times 10 to the 23rd. I'm just saying some people get confused by just putting on the second step. Some people prefer to make it two separate problems that are just one step each. Some people go, I got this. I can just do one problem with two steps. Just wanted to show you both ways. All right. So, like I said, realistically, guys, if you're doing chemistry, if you're doing a lab or anything like that, what you're going to have to do is you're going to have to go from grams to moles, and that's probably it. Then you'll have to do some kind of conversion between moles. That's all. You're really not going to too often have to find the number of molecules or atoms, but it is good practice with our problem solving. All right. Let's take a look at number 3. So number 3 on the worksheet. So again, let's pay attention to our start, and let's take a look at our target so we can kind of visualize the problem, okay? So this time, what they're giving us is 2.3 times 10 to the 24th atoms of silver, okay? 2.3 times 10 to the 24th atoms of silver, which has a symbol that actually comes from the Latin for silver, argentum, which is Ag. That's my nickname, actually. Everybody calls me a G. All right, target. Sometimes I like to have, thank you, Caleb. All right, what is the target? What are they asking me to find? How many grams? Okay, so target, I'm going to put question mark grams. So let's visualize this. What are we doing in this problem? While we know the number of atoms, if I know the number of atoms, I can find the number of moles, right? Okay, if I know the number of atoms, I can find the number of moles. If I know the number of moles, then I can just use the molar mass to find the actual mass of however many moles I have, right? Let's see what it looks like. So again, I'm going to start with what's given. 2.3 times 10 to the 24th atoms of Ag, just over 1, nothing else. Start is never over anything except just 1, all right? That's it. I mean, that's not technically true. For all the stuff we're doing, it is. Right? So if I have atoms of Ag on top, what am I going to put on the bottom then? Atoms on the bottom, that's right. Not only atoms, but atoms Ag, that's right. Okay. Cool. So what is the only conversion factor we have that deals with atoms or molecules? Avogadro's number, right? It says 6.02 times 10 to the 23rd atoms per 1 mole. And in this case, we're dealing with Ag, so 1 mole of Ag. The reason why we always move the units the way we do is so they cancel out. So atoms of Ag canceled. Now, if I stop right here, this will tell me how many moles of Ag that would be. So 2.3 times 10 to the 24th atoms would be how many moles. If I stop right here, I can find that out. Do you guys want me to stop or just continue? Just do the two-step problem, continue on. So just know whatever unit you have that's not canceled out, that's what you've found so far. So stopping right here, we would know moles. But we don't want to know moles. We want to find the mass. So I have moles on top right now, right? So I got to have moles down here. And I know that I want to get to mass. Okay? And again, we only have two conversion factors. We just used one of them was Avogadro's number. Let's use our other new one, molar mass. And it's actually really easy because the substance we're dealing with is just Ag, right? Okay? Ag, according to the periodic table, has a mass of 107.87. So I'm just going to say 107.87 over 1. So that says the molar mass of silver is 107.87 grams per mole, right? And now, because I did that, the moles cancel out. Now the only units I have left are grams. So if I stop here, I should put Ag on there, grams of Ag. If I stop here, I'm going to find the number of grams of Ag. What did we want to find? We wanted to find the number of grams of Ag, right? Cool. All right, so let's just solve it then. I got to find a top answer, and I got to find a bottom answer, and I'm kind of running out of room. So I'm going to bring this down a little bit. All right, I'm going to take it down right here. All right, so multiply across the top. What is 2.3 times 10 to the 24th times 1? Nope, 2.3 times 10 to the 24th times 1 would just be 2.3 times 10 to the 24th. Okay, so just this times this. All right, now what's 2.3 times 10 to the 24th times 107.87? Is it? What is it? Say it again. 248.101. Now let's just say 248.1. All right? You're lost, Caleb? Okay, how'd you get lost? Okay, so I took this thing here. I'm just finding a top answer. All right? I took that times 1, which is just that. Now I'm multiplying it times this. And when we do that, what I do is I take the normal front part, 2.3, and I multiply it by this. So all he did was took 2.3 times 107.87, and he got 248.1. But it wasn't 2.3 times 107.87. It was 2.3 times 10 to the 24th. So after we multiply our normal parts, when we're done, we just write times 10 to the 24th after it. Okay? Cool? Does that make sense to everybody? And let's include our units, grams of Ag. Now we have to multiply across the bottom, which is pretty easy because it's all 1 except for one thing, Avogadro's number. So really the bottom is just going to be Avogadro's number. So similar idea here. We take the normal numbers out front, just divide them normally. So what's 248.1 divided by 6.02? 41.21? Mm-hmm. Yep. Yep. Just divide the front numbers normally. Now what we do is now we write the times 10 part, because we do have a times 10 part, right? We do have a times 10 part. So I'm going to write times 10. Yeah, so when we divide, we got to subtract. 24 minus 23 is 1. That's it. And you're done. So you write that answer, boom, you got the answer. If I wanted to, I have 10 to the first, which is really just 10. I could get rid of that. I could say, hey, it's really just 41.21 times 10. That would really mean that we've got 412.1 grams. You don't have to. Just saying if you want to visualize it, you know. So that's what we're working on now. And I'll tell you, right now this seems like a lot, right? You're going to practice it, you're going to get good at it, and realistically, this problem right here is the hardest thing you have to do all year. So if you're in a position right now where you can kind of get it, you're in really good shape. It's going to take a little practice though before it just, okay? Really, you're dealing with two conversion factors, either particles or mass. Huh?